So, now in order to do this, what we would do is we will do some characterization of the various kinds of nonlinearities. So, let me begin by looking at certain classes of these nonlinearities, and I will show that these nonlinearities can be transformed into a nonlinearity in the 0 infinity sector. Okay. Let me make this clear by some examples. Okay. So, suppose you have a nonlinearity belonging to the K1 infinity sector. Okay. What do we mean by saying that a nonlinearity belongs to the K1 infinity sector? Well, what we mean is, okay, so here is this, oh God, okay, here is this line K1. Let me use a new sheet rather than, okay, so we want to talk about this F, which is in the K1 infinity sector. Okay. So, what we mean by that is, so this is a line with slope K1, and if the nonlinearity is in the K1 infinity sector, that means it lies here and here. So, it could be something like that. Yeah. In other words, the nonlinearity is such that f psi by psi, where psi is the input of the nonlinearity and f psi is the output. This is less than infinity, but greater than or equal to K1. Okay. Now, if you have a nonlinearity like this, we can convert this into a nonlinearity in the 0 infinity sector. Okay. Now, how does one convert this into a nonlinearity in the 0 infinity sector? Well, if you have a nonlinearity in the 0 infinity sector, then the following is true: psi times h of psi is greater than or equal to 0. Now, for a nonlinearity which lies in this sector, this is true, but this is true is the same as saying, okay, f of psi minus K1 of psi. Okay. So, for example, if I look at this particular psi, so this is f of psi, and so f psi minus K1 psi is this portion here, which is positive. On the other hand, if I take a psi which is negative, then f of psi is here, and this is K1 psi, and therefore, this quantity here is in fact negative. This quantity here is negative. So, if now this thing, well, let me put a transpose, is multiplied to psi, then here you see you get a positive quantity multiplying positive. So, the resulting thing is positive. In the left half you have a negative thing multiplying negative. So, the resulting thing is positive. So, for any nonlinearity which lies in the K1 infinity sector, we can say that this condition is always satisfied. Now, if this condition is satisfied, then this is what we do. So, this is slope K1 and you have a nonlinearity like that. And what we had just written was, okay, so the input of the nonlinearity is psi and f of psi is the output of the nonlinearity. So, if you think of this nonlinearity like this, and let me call the input psi and the output is f of psi, then one way we could characterize such a nonlinearity is by this quadratic form, which is f psi minus k 1 psi transpose psi is greater than equal to 0. Okay. Therefore, now if you think of, okay, so this is the output phi. If you think of a nonlinearity, some new nonlinearity which has the same psi as the input, but it has phi tilde as the output, where this phi tilde is really f of psi minus k 1 psi, then this nonlinearity, this new nonlinearity will have the property that phi tilde transpose psi is greater than equal to 0, and therefore, this new nonlinearity, let me call it NL1, is passive. Now, how does one obtain NL1 from NL? Well, one way to obtain NL1 from NL is the following. So, you have the original nonlinearity and it has the input psi, and if it has the input psi, it will give the output, which let me now call it phi. Okay. But you want a new nonlinearity which does not give phi as the output, but gives phi tilde as the output. So, how to get phi tilde as the output? You want to use the same psi as the input. Well, if I take a k 1 here, so k 1 times psi is what I will get. And I use a feed forward, then what I will have here is phi tilde, which is phi minus k 1 psi. And so, now if I think of what is in this dotted box as my new nonlinearity, it has as its input psi and it has as its output phi tilde, and this phi tilde transpose psi is greater than equal to 0. So, this resulting nonlinearity is in fact passive. Now, therefore, this resulting nonlinearity, if it is now connected in a feedback loop with a plant which is strictly positive real, then the resulting system is asymptotically stable. So, let me draw that. So, you have this nonlinearity. So, you have psi and you have k 1 of psi fed forward. Okay, so it is still psi here. So, the original nonlinearity had this output phi, but this new nonlinearity has the output phi tilde. And now, if this phi tilde is connected to some G s, where this G s is strictly positive real and stable, then the resulting system is of course, I mean using our earlier results, whatever we had concluded earlier, using the positive real lemma and so on, we can conclude that this resulting closed loop system is asymptotically stable. But now we are interested in knowing not what can be connected to this new nonlinearity, but what can just be connected to this nonlinearity, what plants can be connected to this nonlinearity, and the resulting system would be asymptotically stable. So, what I am now going to do is I am going to do a set of transformations, and these transformations go under the name of loop transformations, and by loop transformations we can actually conclude, or we can find a much larger class of plants which you can connect to the nonlinearity, and the resulting system would be asymptotically stable.